Hola amigos, so let's continue with rate of climb and gliding flight at page number 419 and 428 of the book we are referring, that is Introduction to Flight, with chapter 6 we are talking about over here. And just before that we just look at the altitude effects on power required and power available, which we did in the earlier session. So here we have power required and velocity variation, power available and velocity, and here power and velocity variation. So power required at sea level is like this. Typically the variation of power required at sea level is this, and with the velocity power required varies like this. So at sea level it is down with respect to this graph, and here the power required is shifting upward, also shifting rightwards, and also rotating clockwise a little bit. And here we are talking about power available in power available variation with velocity. And whenever we talk about available power, we talk in terms of the type of engine that is installed on the airplane. Okay, so power available variation for a propeller engine is this at sea level, and as the airplane moves from a sea level to a height, the power available decreases. So here, as you can see, the power available is decreasing because the amount of density decreases. The amount of thrust available, or the power available to generate the same amount of thrust to overcome drag, will decrease. Okay, so which is why the power available is moving downwards. And here also the power available for jet engine at sea level, if you see, it is a linear variation. Here you can say it is quite constant, but here it is a linear variation. And with aircraft moving upward, the power available here also decreases. Okay, the slope changes from high angle to a lower angle. Okay, so if we see the variation of power available at height and power required at height for propeller engine and jet engine, we will see here that with height the power required moves upward and slightly shifts toward right and clockwise. Here we have plotted this graph upward, okay, and it moved towards right and rotated clockwise. And power available for propeller engine decreases, or say is brought down, and shows a decreased power available variation with velocity, which is shown over here, that power available at a height decreases. So this power required curves moves upward. Here it has been moved upward, which is not clearly shown as the difference over here is shown, but consider it that it has been moved upward, and the power available at sea level moves down. For this we are seeing that power available has been moved down here for propeller engine we are talking about. Okay, and for a jet engine you can see over here that power required is like this. For any given design to overcome drag, power required will always remain same. The power required here, here, and here all are same because the airplane is same. But if we introduce the type of engine, whether it's propeller or jet engine, the power available will change depending upon the type of engine installed on the airplane. So the power available for jet engine we can see over here is like this at sea level, and it has been decreased with a decreased slope. So here we can see a decreased slope, and power required at a height has been shifted from here to here, slightly forward, upward, and clockwise. And their intersections in both the graphs, we will see that this is the point of maximum velocity for propeller engine airplane, and here this is the point of maximum velocity, because power required at height and power available at height intersects at a point at high velocity, which will give us the maximum velocity of the aircraft that it can achieve. And the minimum velocity, if we see, sorry, this curve should be over here, this point I'm talking about should be here. Okay, this is V minimum. Okay, this is not V minimum, this is V minimum. And here if we see, the minimum velocity intersection is here for propeller engine airplane, and stalling velocity is this velocity at which an airplane can fly at sea level but not at a height. Okay, here also the stalling velocity is less than the minimum velocity with which it can fly at a height, so it will not be able to fly at a velocity less than minimum velocity at a height. Keep that in mind. Okay, so now we will continue with rate of climb. And in rate of climb, as we did earlier, like this was the aircraft, it is steadily flying and moving with wings level, and we observed its equation of motion. And here also we will see that the aircraft which is steadily flying is now steadily climbing. Okay, and the thrust is aligned in the direction of velocity with which it is moving, and drag is opposite to the direction of velocity, lift is perpendicular to velocity, and weight is always acting downwards towards the center of earth, and it is climbing at an angle theta. Okay, so V infinity, if we take this velocity vector over here, it is at an angle theta with the horizontal. So horizontal component of velocity will be Vh, and the vertical component is V infinity sin theta. Horizontal component will be V infinity cos theta, and V infinity sin theta will be the vertical component of the velocity that will be telling us about the at what rate the aircraft is climbing. So dh by dt, which is over here, that at what rate it is climbing. Okay, dh by dt is equal to V infinity sin theta, or this is actually the rate of climb. So now we will derive the equation of motion like we did for the steady level flight. So here the thrust force is in the direction of velocity, drag opposite, and weight downwards. So parallel to the flight and perpendicular to the flight forces will be resolved like we did earlier. So thrust, which is in the direction of velocity, T minus D, and W sin theta, T minus D minus W sin theta equals 0, because it is a steady flight, there will be no acceleration. So, and perpendicular to the flight velocity V infinity, we will have L minus W cos theta, which is equal to L equal W cos theta. L minus W cos theta equals 0, which means L equals W cos theta. So for rate of climb, if you observe this t minus w sin theta equation, we will see t v infinity. Basically, we have multiplied this equation by v infinity, and we have taken this on the right hand side, and this gives us t v infinity minus d v infinity equals w v infinity sin theta, and t times v infinity minus d v infinity divided by w will give us v infinity sin theta, and we know that v infinity sin theta is rate of climb. Okay, and rate of climb is also expressed in terms of ds by dt. Okay, and from here we can also compute the time it will take to climb by integrating from height at sea level or any other given point to a height where the aircraft is intend to climb, okay, in the given time period, which is dt. So on integrating, we can compute the time to climb. We will discuss about that in later class as well. And if we see this equation, that rate of climb is t v infinity minus d v infinity divided by w, this tells us that the power available, which is thrust into velocity, minus power required, which is drag into velocity, is the difference, which tells us about the amount of excess power which an aircraft has to climb upwards. Okay, so rate of climb is actually the excess power divided by w. So if we see from the graph here, you can see the power required is this, which is d into v infinity. Power required is equal to d into v infinity, and power available for that v infinity for an aircraft to fly at same velocity, and the amount of thrust with the amount of thrust t, the power available will be thrust into velocity. And for propeller engine, we know it is quite constant. So power required is this and power available is this, and their difference at any point in this graph will give us the excess power, and the maximum excess power will be the highest point of the power available and the lowest point of the power required. So their difference will give us the maximum excess power. Okay, and if you recall, power available for propeller engine is given by eta times p. Eta is the efficiency of the propeller, which is rotating and producing the amount of thrust to fly the aircraft with velocity v infinity, and p is the power of shaft, that is brake horsepower, which is being generated by the engine, that is being transmitted through shaft to the propeller to produce this much power. Okay, so power available is equal to thrust into velocity. And for jet engine, we see that power required will be the same for both, but power available is this. Okay, for jet engine, so the maximum excess power will be the difference between the lowest point of this power required with respect to this power available. So the maximum excess power for both the propeller engine and jet engine can be computed from the graph as well.